Use root tests to determine whether the series absolutely converges, conditionally converges, or diverges. In order to use a root test, what we have to do is find the nth root of the absolute value of whatever's inside the sum. And the limit here has to go to infinity. So the absolute value is just going to get rid of the negative 1 to the nth power because it's going to make it positive. Now I'm going to apply the nth root. So I'm going to take the nth root of both e to the n squared and sine to the 2n power. So e to the n squared, when I take the nth root of that, that's the same thing as raising it to the 1 over n power. And here you have an exponent to an exponent. N squared times 1 over n is just n. So e to the n squared becomes e to the n. Now sine to the 2n power, I'm just going to rewrite it like this. So the 2n is outside, and then I'm going to take the nth root here. So I have 2n times 1 over n. That's going to give me 2. Okay, so now I have to take the limit as n approaches infinity of this limit. In order to solve this limit, I'm going to make a substitution. So I'm going to let u equal 1 over e to the n. And as n approaches infinity, well, we have 1 over infinity, which means u approaches 0. So now I'm going to replace this limit with u instead of n. We said as n approaches infinity, u goes to 0. 1 over e to the n, this whole thing is u. And then e to the n is 1 over u. So that goes on the bottom as just u. Now I'm going to rewrite this. Sine squared is just sine times sine. So I'm going to have sine over u times sine. And if you want, you can use a product rule and say that this is the same thing as sine u over u, and then times the limit u approaches 0 of sine u. Okay. So if you want to be precise, that's what you would have to do. And then you'll say, okay, well, the limit, this limit right here, we know is just 1. And then this limit is 0. And then 1 times 0 is 0. So the limit is 0. And since it is less than 1, the series is absolutely convergent. So this is by the root test. Now we want to use this result and limit comparison test to determine whether the series converges or diverges. So now we have a new series. I guess the difference here is a negative 1 to the nth power, and then there's no e. And everything else is the same. So we're going to compare this new series now with our original problem, except we're going to ignore negative 1 to the nth power. So now we're going to take the limit of these two series, or sequences rather, and then we're just going to divide it. So the top is the series, or the sequence that we're interested in for the new series, and the bottom is from the previous problem. And notice that they both have sine squared, or sine to the 2nth power 1 over e to the n. Those are going to cancel, and so I'm left with the limit as n approaches infinity of n squared over e to the n squared. Now, if you want to show your work for this, you would just have to do L'Hopital's rule twice to show that the limit is 0. But a quick, easy way is to say that the denominator is much, much greater. It's going to go much faster to infinity than the top, and therefore the limit is 0. So since the limit is 0 and finite, the sum, negative 1 to the nth power e to the n squared times sine to the 2n over 1 over e to the n converges. So because the limit is 0 and the sum, or the series from the original problem converges, then by limit comparison test, this new series also converges.